Here's example 5 with the Platt optimization. So a tank is to be constructed by joining a hemisphere to each end of a right circular cylinder. The tank will have a volume of 288 cubic meters. Find the radius of the cylinder that gives the minimum surface area of the tank. Okay, so if you want to copy this worksheet and a copy of these steps that we've been using in the last few examples, go ahead and check the video description. There's a link. Click the link to open up this worksheet. You could download and save and print it if you want. So now this one's going to be a little more complicated. There's kind of there's a lot of little subtleties here that we have to worry about. So it's kind of tricky like that, but it's kind of interesting how it ends up working out. But it's just a little weird, so we do want to be a little more careful here than we have been before. But we're still going to follow these steps here. So step 1, draw and label a picture if possible, and assign variables to all the quantities in the problem. So what do we have? We have a tank that's constructed by joining a hemisphere to each end of a right circular cylinder. So if we were to draw that, so let's draw it in 3D first, or sort of 3D. So we have a cylinder here. Okay. So we got the cylindrical part of the tank, and then on each end of that we're putting a hemisphere. So hemisphere over here, which is just half a sphere, right? And then a hemisphere over here. Okay? So really maybe that should be dotted back there. But anyway, that's what that looks like. So that's, kind of a goofy picture, a little bit difficult to work with, but let's imagine, let's just draw a 2D version of this. So if you take a right circular cylinder, which is this part right here, and if you just look straight at it, what are you looking at? You're looking at a rectangle, okay, in 2 dimensions anyway. Now if you take a hemisphere, so we have hemispheres on either side, if you look at those just directly from the side, what are you looking at? You're looking at semicircles or half circles. Okay. So this 2D version is what's going to be really useful to us. So we have the right circular cylinder viewed from the side, looks like a rectangle, and then on each end of that we're putting hemispheres. And when you view those from the side, they look like little half circles. Okay, so we'll forget about the 3D picture, just totally forget about it, and then we'll have this here. So let's label this. So let's call this X, or if you want to call it H, because it's technically the height of the cylinder if you view it this way. It doesn't really matter, whatever, you can call it whatever you want. And then R is going to be the radius. And it's nice because R is actually the radius of the hemisphere, or the semicircular part here, and R is also the radius of the cylinder. Okay. So that's really good there. Okay, so let's zoom in a bit on that. Okay, so R is just this distance right here, okay, which is the same as this over here, so R is going to be half the distance across here. Okay, so that's really good. Great, great. Let's zoom back out. And also, X is going to be this distance here. Okay. Because, it is a cylinder, so when you view from the side it looks like a rectangle, and since it's a rectangle here, if this is X, then this is also X over here. Okay. So there's our picture that we drew and labeled. Now we want to assign variables to all the quantities in the problem. So R and X we've just assigned, so let's not bother writing them down just to save ourselves some time that we're going to need. And then what else are we talking about? We're talking about volume, but it's a constant, okay? So we don't have to assign it any. If you want to call it V, you could, but it's not going to help you because it's just a constant 288. So we don't really have to call it anything. But we are talking about surface area, okay? Surface area, we want to minimize that. So let's say let S be the surface area. Okay? And if you'd rather call it capital A, it doesn't really matter. It doesn't matter what you call it, it's all going to be the same. So that's really it for step 1. Okay, so draw and label the picture if possible, and assign variables to all the quantities in the problem. Okay, so now step 2, write an equation for the quantity to be maximized or minimized. So we want to minimize the surface area, so we want to write an equation describing it. So what do we have? We have a cylinder with 2 hemispheres. So really the 2 hemispheres, we can just treat them as one sphere. So even though they're not connected to each other, you have half a sphere over here and half a sphere over here. So it's basically like you have one full sphere and one cylinder. It doesn't matter how they're connected, okay, the point is we have 2 hemispheres, so together they make a whole sphere. And the fact that they're split apart makes no difference as far as surface area goes. Okay, so we'll come back to that though. So surface area, we take the surface area of the cylinder, add it to the surface area of a sphere. So remember, for a right circular cylinder with radius r and height x, in this case our height, so to speak, is x, the surface area is 2 pi rx. So in other words, take the circumference of the base and multiply it by the height of the cylinder. Okay, circumference of the base is 2 pi r, height of the cylinder is x, so that gives us a surface area. So S equals 2 pi r x. Okay, now we have to add the surface area of each hemisphere. But remember, two hemispheres together make one sphere, so the surface area, we can just pretend we have a sphere. So for a sphere with radius r, the surface area is 4 pi r squared. Okay. Now, yeah, we have two hemispheres, so for each hemisphere, the surface area is actually going to be 4 pi r squared over 2, but since we have two of them, we add those together and we just get 4 pi r squared. Okay. So no matter how you look at it, we have 4 pi r squared. Okay, so this is the surface area, this one is 4 pi r squared over 2. Surface area, this one is 4 pi r squared over 2. Add them together, you just get 4 pi r squared. Okay? So that's step 2. Write an equation for the quantity to be maximized or minimized. Now step 3, reduce the equation to one with a single independent variable. This may require secondary equations that relate the variables to each other. So remember, this is always the step where we ask ourselves, do we have any other pieces of information that we could use to relate the variables to each other? So what have we not used yet? Well, we haven't used anything about the volume. Okay, so the volume is 288 cubic meters. So we can use this fact to relate R and X to each other and express S in terms of just one of the variables. Okay, so for volume, remember we have a cylinder and two hemispheres, and we can treat the two hemispheres as one sphere. So for a right circular cylinder with radius R and height X, which is what we have here, the volume is pi r squared times X. So in other words, it's the area of the base, okay, the circular base, times the height of the cylinder. Right? That's what the volume is. So pi r squared times x plus, now we have to add the volumes of the hemispheres. So each hemisphere is half a sphere. So remember, for a sphere with radius r, the volume is 4/3 pi r cubed. So this, the volume of this hemisphere is 1/2 of 4/3 pi r cubed. The volume of this hemisphere is 1/2 of 4/3 pi r cubed. Add them together, you just have the volume of one sphere, which is 4/3 pi r cubed for a sphere with radius r. Okay, so add 4/3 pi r cubed, and that gives you the volume of the entire tank, which we're told is 288 cubic meters. So this is 288. Okay. Okay, so now what we have to do is solve this equation for one variable in terms of the other and stick that expression into here. So let's look at these equations here. 2 pi rx plus 4 pi r squared. It's going to be easier on us if we can express x in terms of r, because then we don't have to worry about the squared here. Okay. Now let's look at this equation. Pi r squared x plus 4/3 pi r cubed equals 288. It is much easier to solve this for x in terms of r, because we only have one x here, but here's an r squared, here's an r cubed. So solving for x is going to be tremendously easier, which is great. So it's better to use, it's better to substitute x over here, better to solve for x over here. That's perfect, works out really nicely. The numbers are going to be kind of ugly, but still, it's not going to be too bad. You know, this could happen, especially with, you know, applications of calculus. So anyway, let's solve this for x. So pi r squared x equals 288 minus 4/3 pi r cubed. Okay. Now we divide both sides by pi r squared, so x equals 288 minus 4/3 pi r cubed, all divided by pi r squared. Okay. Now I know I've said in a few videos, a few other videos, that we don't really like having these complex fractions, so we want to simplify them. But for this, it's okay, because this is not a final answer. Okay, this isn't really an answer that we're using for anything. We're just going to take this and stick it into here. So we're going to take this expression for x, and then shove it on up into this equation over here, okay, to get this expression, to get this equation in terms of just r with no x's. So if you want, you could simplify this now, but it's going to be, we don't really want to worry about that now because we're going to simplify later anyway. So let's not worry about it too much here. Okay, if you want to, you can, but it's just a little extra work that doesn't really need to be done. So anyway, s. We're going to come down here because we need a lot more room. So now s of r, okay, because we're going to express this in terms of just r, equals, so we still have a 2 pi r. Now what about x? X becomes, so this x here becomes this big nasty expression here. 288 minus 4/3 pi r cubed. 288 minus 4/3 pi r cubed. Remember, all of that was being divided by pi r squared. Okay, and then we still have plus 4 pi r squared out here. Okay, so this is great because now s is expressed in terms of just r, so that's why we write s of r over here. Okay, so remember, we're still on step 3 here, reduce the equation to one with a single independent variable. So that's what we're doing now, and we used our secondary equation here about the volume. So here's our secondary equation, solve that for x in terms of r, take this expression, shove it into this equation here, we end up with this, now we simplify. Okay, so 2 pi r, if we distribute that into the parentheses, first of all, this pi cancels with this pi, that's great. This r cancels with one of these r's down here. So what we really have is just 2 being distributed up to the top here. So 288 times 2 is going to be 576, so this is 576 minus 8/3 pi r cubed, all divided by r, okay? And then plus 4 pi r squared. So now let's split this up into two fractions. So 576 over r, and then minus 8/3 pi. So this is r cubed over r, which just becomes r squared. Okay, so we just took this fraction, split it up into two. 576 over r minus 8/3 pi r cubed over r becomes r squared. Okay, 8/3 pi r squared, and then plus 4 pi r squared. Okay, now there's some more simplifying we could do. So remember, this is all just s of r, s of r. Now remember, it's applied optimization, so we know eventually we're going to take a derivative. So what I want to do is rewrite this as 576r to the negative first power. Why am I doing that? And the reason is, so eventually when I take a derivative, I can do power rule instead of quotient rule. Okay, power rule is better in this sense than quotient rule. Okay, so that's why I'm doing that. Now what about this? This is kind of a mess. Minus 8/3 pi r squared plus 4 pi r squared. Let's come up here. Minus 8/3 pi r squared plus 4 pi r squared. So first of all, there's a common factor of r squared we can pull out. So what we have is minus 8 pi over 3 plus, now 4 pi is the same thing as, so if we multiply the top and the bottom by 3, put a 3 on the bottom, multiply the top by 3, 3 times 4 pi is 12 pi. On the bottom we have a 3, okay? And we're pulling out this r squared from both, okay? So what I did 2 steps in one here. I pulled out the r squared and I got a common denominator. Okay, 4 pi is the same thing as 12 pi over 3. So then when we simplify this, minus 8 pi over 3 plus 12 pi over 3, that becomes 4 pi over 3. So that's 4 pi over 3 times r squared, okay? So minus 8 pi over 3 r squared plus 4 pi r squared. This whole thing becomes plus 4 pi over 3 r squared, okay, from this. So this is a positive 4 pi over 3 times r squared, which is why we have plus 4 pi over 3 r squared. Okay, so that's where that came from. So, just, it's kind of tricky, kind of messy. You got to be careful with your pi's and r's flying around all over the place here. So the algebra is kind of, a little more complicated than the previous examples anyway. So anyway, that's step 3. Reduce the equation to one with a single independent variable. This may require secondary equations that relate the variables to each other, so that's what we did. We used the secondary equation here about the volume, solved it for x in terms of r, took that expression, shoved it into this equation here, got this big mess, simplified, ended up with this. Okay. Now step 4, find the domain of the equation found in step 3. Now this is where things get a little tricky. We have to be really careful here. So remember, r represents a length or a distance, so it has to be strictly positive. What if r is 0? Then the cylinder has no radius, the hemispheres have no radius, nothing is happening, nothing exists. So, physically that's possible, but really it just doesn't make any sense to have that because then nothing is happening. Okay? So for the domain, we have to have r greater than 0. Okay? Now also, so that's what I just wrote here, domain has to be r greater than 0, but also x should be positive, right? Because x also represents a length or a distance. But 2 things here. First of all, we can't just say that. We have to express this in terms of r, because the equation we got in step 3, we reduced the equation to one with a single independent variable. Our independent variable is r. So the domain of the equation found in step 3, the domain has to be expressed in terms of r. So first of all, it's not okay to say this. But second of all, here's where things, we have to worry about these little subtleties here. Things get a little bit different. X actually can be 0. Why can x be 0? Well, if x is 0, what does that mean? That means the cylinder has no height. So if the cylinder has no height, the cylinder just completely goes away, but we still have 2 hemispheres. Okay, so actually what happens is if the cylinder goes away, we have this hemisphere and this hemisphere that come together with no cylinder in between them. So really, we just have a sphere, right? So hemisphere over here, that come together to form a perfect sphere with no cylinder in between because x is 0. Okay, so it's actually okay for x to be 0. So before we had to toss all these cases out, like here, r can't be 0, because if r is 0, nothing's happening. Okay, the cylinder doesn't exist, the hemispheres don't exist, but so then nothing exists, nothing's happening. But if x is 0, yeah, the cylinder doesn't exist, but the hemispheres still do, so that is possible. So it's kind of goofy, when you think about that, the way the problem was phrased, especially because we're talking about joining hemispheres to each end of a right circular cylinder tank. But physically it is possible to have x be 0. Physically it is possible, so we do have to consider that case. So really, really subtle detail to worry about there. Kind of goofy, but it is what it is. We just got to roll with it. So x greater than or equal to 0. But remember, we have to express this in terms of r. How do we do that? We go back to our secondary equation here that we solved and use this expression. So this fact. Okay, this is how x and r relate to each other, always. So this fact, combined with the fact that x has to be greater than or equal to 0, means, since x equals this mess up here, then that means that 288 minus 4/3 pi r cubed divided by pi r squared has to be greater than or equal to 0. Okay, because we know x has to be greater than or equal to 0, but x equals this big mess here. So this has to be greater than or equal to 0. That's going to give us a new restriction on r. Okay, so first of all, pi r squared, that's always positive, right? So we don't have to care about that. So we can multiply both sides by pi r squared. 0 times pi r squared is just 0. So cancel, cancel. 288 minus 4/3 pi r cubed is greater than or equal to 0. So then 288 is greater than or equal to 4/3 pi r cubed. Okay, so now what we want to do is multiply both sides by, so let's rewrite this like this. So this is a 4, all right, let me do this. 288 is greater than or equal to 4 pi over 3 times r cubed. Okay, so now let's multiply the right side by 3 over 4 pi, and then multiply the left by the same thing. Okay, so 4 pi cancel with 4 pi, 3 cancel with 3, that's great, so all we have left is the r cubed, that's wonderful. Now 3 over 4 pi times 288, so you can toss that to a calculator, but that's going to give you 216 over pi, and that's greater than or equal to r cubed. Okay, so kind of running out of room over here, so what I want to say is, well, now we want to solve for r, right? So we're going to take a cube root of both sides, or in other words, raise both sides to the 1/3. Okay. Okay, so now r cubed to the 1/3 is just r, so we have r on this side. 216 to the 1/3 is 6. Okay, the cube root of 216 is 6. Okay, so in other words, 6 times 6 is 36. Multiply by 6 again, you get 216. Pi to the 1/3 is just pi to the 1/3. So that's our new restriction here. R has to be less than or equal to, so let's write it like this, r has to be less than or equal to 6 over pi to the 1/3. Okay? And 6 over pi to the 1/3 is about 4.097. Is that right? Yeah, it's about equal to that. So here's our upper bound for r. So the domain in interval notation is going to be 0 to 6 over pi to the 1/3. So this time, open parentheses around the 0 because r cannot be equal to 0, but r can be equal to 6 over pi to the 1/3. Okay? So here's our domain restriction here. Okay? And again, why is r allowed to be equal to that? Because x is allowed to be 0, because if x is 0, you just have a sphere, okay, 2 hemispheres to make a sphere with no cylinder. And yeah, that is kind of goofy, but physically it is possible, it could happen, so we have to consider it. Okay? All right, now, that's it for step 4. So really subtle detail there to worry about, so that could happen sometimes, just be very careful. Step 5, use calculus techniques to find the desired quantity. Okay? So now that means we're just going to start taking derivatives, because what do we want to do? We want to minimize the surface area. We want to find the radius of the cylinder that gives the minimum surface area of the tank. Okay? So we're talking about minimizing the surface area, so we're going to, and the surface area is given by this equation here, where r represents the radius of the cylinder, or radius of the hemisphere, same thing, right? They're the same radius. So let's take a derivative. So s primed, so let's block that off, s primed of r equals, so remember when we wrote this like this, now we're going to do power rule instead of quotient rule, so that's a little bit easier on us. So this is minus 576 r to the negative 2, and then this is going to become plus 8 pi over 3 times r. Okay? So now we want to know when is the derivative 0, when is it undefined. So we're looking for critical points, right? So that's what we have to do. So now we're going to rewrite this as minus 576 over r squared, and then this is plus 8 pi over 3 times r. Now we want to get a common denominator, so let's multiply this guy by r over r. Okay, so this is a minus 576 plus 8 pi over 3 r squared, all divided by r squared. Okay, so that's what's happening over here. All right, I'm sorry, hang on. 8 pi over 3r, so we have to multiply by r squared on top and r squared on the bottom because the common denominator is r squared, okay? So this is minus 576 over r squared, this is 8 pi over 3 times r, okay? So we have to multiply this by r squared over r squared. I'm totally out of room over here, so let's come back, let's come to the back side. So s prime of r equals, and you know, let's do that again less confusingly, so sorry about that. Minus 576r to the negative 2 plus 8 pi over 3 times r, okay? So this is a minus 576 over r squared, and then plus 8 pi over 3 times r. Okay, so really we can think of this as 8 pi over 3 times r, all of that divided by 1. Okay, so denominator here is 1, denominator here is r squared. So multiply this by r squared over r squared. Okay, sorry about the confusion. So this is minus 576 over r squared plus, now this is over r squared. Right? And then on the top, what do we have? 8 pi over 3 times r cubed. Okay, so you see, that's why these complex fractions are really nasty and kind of tricky, but sometimes they're unavoidable. You know, we could push the 3 into the bottom, but let's not get too crazy here. Not worry about that. Okay, so now this equals minus 576 plus 8 pi over 3 times r cubed, all divided by r squared. Okay. So that's a 3 right here. Okay, now this equals s prime of r. Okay, we want to know when is this guy 0, when is it undefined? Well, first of all, it's undefined when r is 0. But is r allowed to be 0? No, that's not in the domain. Okay, r has to be strictly greater than 0. Because remember, if r is 0, then no radius, which means no cylinder and no hemispheres, so nothing's happening. Okay, so we cannot have that. Okay. So we toss that one out, so that's not a critical point, it's not the domain. Now we want to know when is this equal to 0. So we take that big expression, set it equal to 0, and solve for r. So minus 576 plus 8 pi over 3 r cubed, all divided by r squared equals 0. Remember, a big nasty expression like this equals 0 when the top is 0, so forget about r squared, or you know, in other words, you can multiply both sides by r squared, which is okay because we know r can never be 0, so that's okay to do that. But no matter how we think about it, we end up with this, minus 576 plus 8 pi over 3 r cubed equals 0. Let's add 576 to both sides. Let's multiply both sides by 3 over 8 pi. Okay. So 3's cancel, 8 pi's cancel, we have r cubed over here. Now 576 times 3 over 8 pi is actually going to give us 216 over pi. Okay, so that's kind of interesting, right? If you're not sure why that's interesting yet, just hold that thought. So now we want to raise both sides to the 1/3. So r equals 216 to the 1/3 over pi to the 1/3. And remember, we talked about it before, 216 to the 1/3 is 6. So this is 6 over pi to the 1/3. So we know that when r equals this, the derivative is 0. So in other words, that's a critical point. Well, is it a critical point? Is this in the domain? 6 over pi to the 1/3. Yeah, that's barely in the domain, right? That's the end point here. And remember, r is allowed to be equal to 6 over pi to the 1/3. Because if r equals this, then that's the same thing as saying x equals 0, right? So remember, x could be greater than or equal to 0, x being the height of the cylinder. Because if x equals 0, then there's no cylinder, but we still have the spheres, the hemispheres, that form together, that come together to form one sphere. So that could happen, and x equals 0 when r equals 6 over pi to the 1/3, which is actually our critical point. Okay, so that's interesting there. Now, what do we want to know? Remember, we're talking about minimizing the surface area. So again, just by the nature of the problem, the question we're asked, you know, it's probably going to give us a minimum, but you know, otherwise the problem just doesn't make sense the way it's asked. But we still have to be very thorough, be very careful about everything. So what we're going to do is just continue to go through the motion. So let's do the second derivative test like we usually do, because the first derivative test, it'll work, but it's going to tell us stuff about increasing and decreasing. We don't really care about that. It's just more work than we have to do to get more information that we need. So why bother with that? Let's do the second derivative test. So remember, s primed of r equals negative 576 r to the negative 2 plus 8 pi over 3 times r. So then s double primed of r equals 576 times 2 is 1152. So negative 576 times negative 2 is positive 1152 times r to the negative 3. So again, that's just power rule, right? Just a regular old power rule, plus 8 pi over 3, and then that's it. So 8 pi over 3 r, the derivative is just 8 pi over 3. So now let's rewrite this as 1152 over r cubed, and then plus 8 pi over 3. Okay, so we're doing the second derivative test, so that means take this critical point, toss him into here. So s double primed of 6 over pi to the 1/3 equals 1152 over 6 over pi to the 1/3 cubed plus 8 pi over 3. Ugh, what a mess, right? But that's okay. Why is that okay? Because we don't care what this value is. We don't care about simplifying this. All we care about is, is it positive or is it negative? So let's look at this. 1152, positive number. 6 over pi to the 1/3, positive number. Raise that to the third power, positive number. Positive number divided by a positive number is a positive number. Add another positive number, what do you get? You get a positive number. Okay, so in other words, this is the big nasty mess, lots of crazy numbers here, but everything's positive. 1152, positive, 6, positive, pi to the 1/3, positive, raised to the third power, positive, divide positive numbers, positive, add a positive number, positive. Everything's positive. So what does the second derivative test tell us? So then by the second derivative test, s of r has a local minimum when r equals 6 over pi to the 1/3. Okay? And that's it, right? That's it for the problem, because the problem asked us find the radius of the cylinder, which is the same thing as the radius of the hemisphere. Find the radius of the cylinder that gives the minimum surface area of the tank. And that happens when r equals 6 over pi to the 1/3. That's what the second derivative test just told us. So r equals 6 over pi to the 1/3. And the units were meters, right? Because the volume was cubic meters, so the units for r have to be meters. So m for meters, okay, m for meters. And remember that was approximately, so you should be exact as much as you can, as often as you can, whenever you can, for as long as you can. And we can be exact the whole way here, but that's approximately equal to 4.097 meters. Okay? So that's it for this problem here. Now let's analyze this for a sec. So remember, if r is 6 over pi to the 1/3, what does that mean? Remember, that means that x equals 0, right? So x is greater than or equal to 0 when blah, 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 r is less than or equal to 6 over pi to the 1/3. So x equals 0 when r equals this 6 over pi to the 1/3. And we actually just found out that when r equals that, that gives us the minimum surface area. Does that make sense? Yeah, that absolutely makes sense, because if r is that number, then x is 0, and if x is 0, there's no cylinder. So if there's no cylinder, all we have is the two hemispheres that come together to make a sphere. That's as small as we could possibly have, right? So that's going to give us the minimum surface area. Because if x is anything larger than 0, then we're going to have a tiny little bit of cylinder in there. And if we have a tiny little bit of cylinder, that's more surface area. Okay, so as it turns out, we're going to have a minimum surface area when there's no cylinder, right? Now that's really, really, really goofy, just the way the question was phrased, because we're talking about joining a hemisphere to each end of a right circular cylinder. So we'd expect to have the circular cylinder. So, but and the answer to the question, when r is this value, x is 0, which means there's actually no cylinder. So it's really strange, really goofy, just, I don't know, just so weird. But it is something that could happen physically, so we do have to be careful about that case there. So no cylinder, two hemispheres come together to make a perfect sphere, and that's when we have the minimum surface area. And that is precisely when r has this value. So that's it for example 5 with applied optimization. So again, just to summarize real quick, just to rephrase the answer, the surface area is minimized when the radius of the cylinder, or the radius of the hemisphere, same thing, when the radius is 6 over pi to the 1/3 meters, which is about 4.097 meters. So that's it for example 5 with applied optimization.